December 10th, 1941, Washington, D.C. In a meeting room of the War Department, the weak winter light could only reach the edge of the long table where weather maps and field reports were piled up. Brigadier General Eugene Raybould stood there, reading the same lines again and again, lines no one in that room wanted to believe. 3 days after Pearl Harbor burned, the United States was facing an enemy no one had talked about. Not Japanese planes, not naval guns. It was the weather. Tropical rain was doing what bombs could not. Canvas tents were falling apart in less than 3 weeks. Supply areas were flooded. Hundreds of soldiers were sent to medical units with pneumonia after their tents collapsed in the rain. Reports came from the Philippines, from Wake Island, from every small coral atoll where Americans were trying to hold on to ground they had just taken. An officer standing near the window, his voice rough with worry, said it in a way everyone could understand. "We have 48,000 men sleeping in tents that will last 3 weeks. The Navy says we need 18 months to build wooden barracks. We don't have 18 months. The numbers were brutal. A standard Army tent cost $12 and survived about 1 month in jungle weather. A wooden barracks cost $8,000 and needed 6 weeks and skilled carpenters. Both were useless when you needed shelter for 50,000 men. Yesterday." Then, in that quiet room where you could hear a pen touch the table, someone wrote down a different kind of idea. Not a wooden building, not another tent. Something that did not exist yet. A structure that could be packed flat, shipped halfway around the world, and put up in a few hours without skilled workers. The only thing they did not know was how to build it. 2 months later, in Rhode Island, 30 engineers started a race against the impossible, and they had only 60 days. The Nissen Hut blueprint arrived at the Navy's Bureau of Yards and Docks in one of those peculiar wartime twists. British engineers, grateful for American supply shipments, shared detailed technical drawings of their World War I shelter design. Semicircular tunnels, 16 feet wide, made from corrugated iron sheets bolted to a wooden frame. Commander John Philip Drosfeld studied the specifications with the careful eye of a man who understood that lives depended on whatever came next. The genius revealed itself immediately. The arch shape naturally deflected wind and shed water without complex engineering. But the problems became equally apparent. The British huts weighed 3 tons when disassembled. They required foundation bolts drilled into concrete. That internal wooden frame would become a termite feast in tropical climates, and 2 small windows designed for Scottish weather would turn these structures into ovens at Guadalcanal's 98-degree average temperature. Drosfeld's red pen circled the ventilation specifications. The annotation in the margin may have read simply, "Brilliant for France 1917, suicide for Guadalcanal 1942. But there was another voice in this conversation. Buckminster Fuller had been preaching prefabricated housing since the 1920s, though most architects dismissed him as impractical. His Dymaxion house, factory-built, lightweight, assembled on-site, suddenly sounded less crazy when the country needed to build a city's worth of shelter every month. The military hadn't directly consulted Fuller, but his published papers circulated through engineering departments. His core insight proved invaluable. Treat buildings like manufactured products, not construction projects. The Navy consolidated this thinking at Quonset Point, Rhode Island. The location wasn't random. Rhode Island had deep sheet metal expertise from its jewelry and silverware industries, and sat close to Pennsylvania steel mills and shipyards, where engineers understood corrosion resistance through hard experience. In March 1942, the Navy assembled an unusual team. Structural engineers from Strand Steel Corporation, architects from George A. Fuller Construction Company, and Navy officers who'd served in the Pacific and knew what typhoon-proof meant in practice. Otto Brandenberger led the team, bringing farm building experience that proved exactly right for this problem. His barns used self-supporting arched panels with no internal frame, no wood for termites, no complex joinery to fail during storms. Brandenburger's proposal sounded radical. Eliminate the Nissen hut's wooden skeleton entirely, and make the corrugated steel skin carry all loads by itself. Steel was for bridges and skyscrapers, not self-supporting buildings that ordinary men would bolt together on beaches. But Brandenburger had walked through tornado aftermath, where his barns stood intact, while conventional structures became kindling. An engineer later recalled him saying, "My barns survive Midwest tornadoes without internal framing. An arch doesn't care whether it's holding up corn or marines. The British contributed crucial intelligence through painful experience. Their reports from Burma and Singapore weren't just technical documents, they were lessons written in failure. Fungus ate through preservatives within months, humidity corroded fasteners until roofs collapsed, carpenter ants hollowed beams in a season. Those reports became a checklist. No wood touching ground, all steel hot dip galvanized, ventilation aggressive enough to prevent condensation, every fastener replaceable." By April 1942, the vision crystallized. Take the Nissen arch, strip everything heavy or vulnerable, add Fuller's mass production logic and American industrial muscle, and engineer every detail for Pacific warfare. The pieces were assembling. Now they had to prove it worked. Mid-1941, at Quonset Point, Otto Brandenburger and a small Navy Fuller design crew faced a nearly impossible assignment. 60 days to create, prototype, and approve an entirely new, prefabricated hut for the Navy's rapidly expanding bases. At Quonset Point, a small team from the Navy's Bureau of Yards and Docks and George A. Fuller Company worked almost continuously in the assembly shops, turning sketches into prototypes under wartime pressure. Brandenburger divided his crew into specialist teams. One tackled aerodynamics and structural loading. Another figured out nesting components for shipping. A third worked exclusively on joints and fasteners that had plagued the British design. The first radical decision came on day 3. Traditional architectural drawings took weeks to produce. The team didn't have weeks. Instead, they built in real time. Sketch a detail in the morning, have the metal shop fabricate it by afternoon, test it overnight, revise by dawn. This iterative approach is standard now in 2025. But it was revolutionary in 1942 when buildings were designed completely on paper before cutting a single piece. The warehouse floor became a laboratory, telling stories through debris. Failed joint experiments, bent test panels, each refined version documenting evolution measured in metal rather than drawings. The engineers borrowed from aircraft manufacturing. Every part numbered, every revision documented, nothing advancing without solving previous failure points. Dimensions came from brutal practicality. Standard huts measured about 20 by 48 feet, roughly 960 square feet of usable space, large enough for 30 to 40 men, or conversion to offices and infirmaries, 48 feet total length, housing 36 men with bunks, or converting to offices, medical stations, supply storage. This size hit a sweet spot in structural engineering. Smaller wasted shipping capacity. Larger made panels too heavy for field assembly, or required internal supports reintroducing all the eliminated problems. The arch radius calculation consumed 2 full weeks. Too flat and wind could peel the structure like opening a can. Too steep wasted headroom while creating difficult end-wall geometry. Brandenburger's team settled on an 8-foot radius, a perfect semicircle providing 7 feet of headroom at sides, creating what engineers call a self-bracing arch. The corrugated steel naturally wanted to hold this curve, allowing thinner, lighter panels than flat sheets required for equivalent strength. Load calculations showed the design could theoretically handle snow loads up to 40 pounds per square foot and wind speeds exceeding 100 miles per hour. But an engineer working late one night may have noted in his journal, Calculations say it works. Pacific typhoons are different animals. We'll learn when lives depend on it. By day 40, they had something resembling success. The first complete prototype went up May 25, 1942, assembled by 6 sailors given 4 hours of instruction and basic hand tools. Assembly time, 14 hours. Encouraging, but not good enough. The Navy wanted single-day construction because marine landing schedules didn't allow multi-day projects. The team identified the bottleneck immediately. They'd been including a wooden floor, thinking men needed something to walk on. But it was the slowest assembly part, and first thing to rot in tropical conditions. The solution carried elegant simplicity. Eliminate the floor entirely from the basic design. The hut sits directly on whatever surface exists: coral, sand, dirt, gravel. For applications requiring finished floors, those could be added later separately. But basic shelter achieved weather protection without them. This single decision cut assembly time to 8 hours and reduced shipping weight by 1,200 pounds per unit. June 10, 1942, the final prototype stood complete. 96 corrugated steel panels, each under 50 pounds, bolting together to create 720 square feet of enclosed space. Each hut cost roughly $800 to $1,000 in materials and weighed several tons depending on fittings. Remarkably cheap and light for a building that could be shipped anywhere. The real test was beginning. Navy structural engineers arrived carrying wind load tables, typhoon data from Pacific meteorological stations, and healthy skepticism that this corrugated tunnel could survive what nature threw at tropical islands. The numbers weren't theoretical exercises. They came from actual events that killed people and destroyed cities. Typhoon Gloria hit Guam in November 1940 with sustained winds of 140 miles per hour and gusts reaching 180. The 1935 Labor Day hurricane killed 400 people in the Florida Keys with winds that sandblasted paint off buildings and drove wooden planks through palm trees like spears. If Quonset huts failed in storms, the result wasn't property damage. It was dead servicemen and destroyed equipment. A Navy engineer who'd survived the 1935 hurricane may have stated during those sessions, "My job is making sure failure doesn't happen when it means American lives." Brandenburger's team explained the fundamental physics. When wind hits a flat wall, it creates maximum pressure coefficient, pushing directly with full force. But curved surfaces deflect wind upward and around, reducing pressure dramatically. Think of water flowing around a river stone versus slamming into a dam wall. The semicircular Quonset profile meant hurricane winds would slide over rather than punch through. The corrugations added another layer. Those lengthwise ridges created structural rigidity, the way folding paper makes it stronger. Each corrugation acted like a tiny I-beam, resisting bending forces that would crumple smooth metal. Load distribution through the arch changed everything. Conventional rectangular buildings have roofs pushing down on walls, walls pushing down on foundations. Storm winds can literally lift roofs off because they're separate elements just sitting on walls. The Quonset arch was a single continuous curve where every panel shared load with neighbors. Engineers call this a compression ring, the same principle keeping stone bridges standing for centuries without mortar. Each panel bolted to adjacent panels with 3/4-inch steel bolts every 6 inches, creating essentially a 48-foot steel cable wrapped in arch shape. But theoretical strength meant nothing without testing. The Navy built a full-scale Quonset at Davisville, Rhode Island, instrumenting it with strain gauges, pressure sensors, deflection meters. Then they waited for the first major nor'easter. March 3, 1943, nature obliged with 75-mile-per-hour winds and heavy snow. Instruments recorded the structure, flexing less than 2 inches at the crown, then returning to original shape when wind subsided. Panel joints held. Nothing leaked. The structure behaved exactly as calculations predicted. thrilling and terrifying because it meant betting thousands of lives on calculations that could have been wrong. Tropical environment testing proved more challenging. You can't simulate years of jungle conditions in a Rhode Island warehouse. The Navy shipped a test unit to the Panama Canal zone, 85% humidity year-round, temperatures above 80 degrees. 6 months later, the report arrived. Minimal corrosion on galvanized panels, no structural degradation. But serious condensation problems. When hot, humid air hit relatively cooler steel at night, water literally rained from the ceiling inside. The solution required adding ventilation louvers at both ends and along the ridgeline, openings letting hot air escape and creating airflow without compromising structural strength or weather protection. These vents added $47 to unit cost, but transformed the hut from steel sauna into habitable space. The final challenge: anchoring 9,000-pound buildings to loose sand or coral without pouring concrete. The answer came from tent technology scaled up, steel stakes driven into ground, connected to hut bases with adjustable tension cables. For harder surfaces, bolt patterns let huts mount directly to wooden sleepers or pierced steel planking. The beauty of this system was forgiveness. The structure could flex slightly with ground movement without tearing itself apart. June 1942, the War Production Board approved manufacturing. American industrial capacity was about to operate at absolute peak. The Navy contracted with 10 major steel fabricators across the Midwest and Northeast. Companies making grain silos 6 months ago suddenly retooled entire factories for military shelter production. Strand Steel Corporation converted its entire Penrose facility outside Philadelphia to exclusive Quonset production. George A. Fuller Construction took over a former automobile parts plant in Chicago. Great Lakes Steel dedicated 2 rolling mills to nothing but corrugated panel production. By August 1942, these factories collectively produced 1,500 complete huts per week. The number kept climbing as production lines refined processes and workers learned efficiency through repetition. The manufacturing process borrowed from automotive assembly line logic. Massive steel coils arrived by rail, 4 feet wide, each containing enough steel for 30 panels. Rolling machines corrugated flat steel, creating ridges at precisely 2.67 inches on center. The corrugating process work-hardened the steel, making it stronger than flat sheet through molecular structure, changes from bending stresses. Next, panels went through galvanizing tanks, dipped in molten zinc heated to 850 degrees Fahrenheit. This wasn't paint that could chip. It was metallurgical bonding, where zinc molecules fused with steel molecules, sacrificing itself to corrosion over years, protecting underlying steel from saltwater air and humidity. The process cost an extra $112 per hut, but field reports would later show ungalvanized steel corroding through in 8 months, proving the expense non-negotiable. Each complete hut kit got packaged with obsessive shipping attention. 96 corrugated panels nested inside each other like stacked bowls, reducing package height from 8 feet to just 14 inches. End walls, plywood sheets with pre-cut door and window openings, packed flat between steel panels. All fasteners, bolts, and hardware boxed in a single wooden crate, including illustrated assembly instructions designed for men who might not read English fluently. The entire kit loaded onto one standard 40-foot flatbed rail car. This packaging density was crucial because every train heading to West Coast ports carried either Quonset huts, ammunition, food, or vehicles. Zero room for inefficient cargo when supplying a war fought 6,000 miles across the world's largest ocean. A logistics officer planning these shipments may have reflected late at night. Every cubic foot matters. If it doesn't fit perfectly, it doesn't ship. And if it doesn't ship, men die. Trains left Philadelphia and Chicago daily, arriving at San Francisco, San Diego, and Seattle, where Liberty ships waited. Longshoremen loaded complete huts using crane systems designed for tanks. Liberty ships leaving West Coast ports often carried large consignments of Quonset hut kits alongside vehicles and ammunition, so that entire advance bases could be erected soon after landing. The Warshipping Administration tracked every manifest because these weren't just buildings. They were strategic assets. A hut shipping to Guadalcanal in September might house a bomber crew by October, making the difference between operational aircraft and pilots too exhausted to fly effective missions. The assembly process on the receiving end showed where Quonset design genius really shone. Navy construction battalions, the famous CBS, developed standardized procedures, turning shelter erection into choreographed operations. 6-man crew, 8 hours. 1 complete hut ready for occupation. Site preparation, level ground, remove vegetation, lay gravel base if available. 2 men handled end walls while 4 wrestled steel panels. Panels overlapped 6 inches and bolted together with 3/4-inch fasteners. No welding, no concrete, no skilled trades, just wrenches, a level, and men following illustrated instructions. The speed record got set on Espiritu Santo in January 1943, when a specially trained CB crew erected a complete hut in 4 hours, 17 minutes. But the real achievement was sustained production across hundreds of islands, where crews threw up 5 or 6 huts per day, day after day, building entire bases faster than Japanese could bomb them back to rubble. By December 1943, monthly production hit 8,000 units. The logistics network moved so efficiently that huts ordered in Pennsylvania reached New Guinea within 40 days, including ocean crossing and trans-Pacific transport. The cost accounting told the victory story. Each Quonset hut provided 36 men weatherproof shelter for $1,394 in materials and approximately 60 man-hours of assembly labor. Compare to conventional barracks, $12,000 in materials, 400 man-hours of skilled carpentry, 6 weeks construction time. The Quonset delivered shelter at 1/10 cost in 1/20th time. By mid-1944, the United States military had deployed over 160,000 units to every combat theater, housing capacity for nearly 6 million personnel built in less than 2 years. But the real test wasn't in factories. It was coming to islands whose names would enter American history written in blood and sacrifice. Guadalcanal, August 1942. The first combat-deployed Quonset huts arrived on a beach where temperature hovered at 95 degrees with 90% humidity. Japanese bombers made daily visits to crater anything resembling American infrastructure. Marine engineers unloaded flat-packed steel panels under sporadic artillery fire, the distant crump of explosions punctuating their work. They assembled in a coconut grove, still showing scorch marks from the previous week's shelling. Metal panels felt hot enough to brand flesh where they'd sat in tropical sun. Within 12 hours, Henderson Field had 10 new structures housing maintenance crews for battered F-4F Wildcats. 3 days later came the real test. A Japanese bombing run scored what should have been a killing blow. A 500-pound bomb detonated 40 yards from a hut full of aviation mechanics. The blast wave flattened surrounding palm trees and shredded canvas tents like tissue paper. The Quonset flexed. Dirt and shrapnel rattled off corrugated steel like hail on a tin roof. When smoke cleared, the structure stood intact. Every man inside was shaken, some bleeding from burst eardrums, all covered in dust. But alive. A mechanic crawling out afterward may have said what many were thinking. Thought the whole thing would come down, but the roof held. The jungle environment proved as hostile as enemy action. Within 2 weeks, red rust streaks appeared on any ungalvanized fasteners. Salt air ate through standard hardware like acid. Fungus grew on everything holding moisture, turning inside surfaces into black and green mold that smelled of rot. Ventilation louvers barely moved the suffocating air. Marines started propping doors open 24 hours and cutting additional vent holes with tin snips, violations of structural specifications, but necessary for livability. These field modifications got documented and sent back to Quonset Point, where engineers incorporated them into later production runs. More ventilation, larger louvers, every single fastener galvanized regardless of location. Iwo Jima, February 1945. The volcanic island offered different hell. Black sand blew into every crevice. No topsoil existed for grounding stakes. Constant artillery threat from Mount Suribachi meant every moment carried possibility of sudden death. CBs arrived on D-Day +2 and started assembling Quonset huts under fire, literally bolting panels together while mortar rounds impacted 200 yards away. The volcanic sand proved impossible for traditional stake anchoring. Stakes driven into black grit just pulled out. So crews improvised, filling empty oil drums with sand and using cables to connect drums to hut bases. Hundreds of pounds of ballast that couldn't pull free. In March, a Pacific typhoon hit with winds measured at 110 miles per hour. Those improvised anchors held while wooden structures across the island disintegrated. The base commander's report to Pearl Harbor was succinct. Quonset hut survived. Everything else gone. Alaska's Aleutian Islands brought opposite extremes. Dutch Harbor and Adak, where temperatures plunged to -40 and winds regularly exceeded 100 miles per hour. Cold made steel brittle. Early units suffered panels cracking at bolt holes. Engineers responded by specifying cold rolled steel with different metallurgy for Arctic deployments, adding rubber gaskets at every joint. But heating created new problems. Warm air meeting frozen steel produced condensation that literally rained inside. Crews learned to install insulation blankets and run ventilation even in sub-zero weather. By winter 1943, weatherized models included internal insulation batting, double wall construction, and modified ventilation preventing heat loss while managing moisture. Super Typhoon Cobra delivered the ultimate test in December 1944. The storm hit the Philippines with winds at 140 miles per hour and 20-foot storm surge. At Tacloban, the storm destroyed 80% of all base structures. Wooden buildings exploded into splinters. Concrete block structures collapsed. Of 43 Quonset huts on base, 39 survived intact, and 4 suffered repairable damage. Bent panels and torn seams, but no total failures. Engineers analyzing survivors found proper anchoring mattered more than any other factor. Huts with adequate ground attachment rode out storms. Those with improvised or insufficient anchoring rolled across landscapes transformed into alien wastelands. By war's end, field performance data from 50 combat zones fed back into continuous design improvement. The 1945 production models bore little resemblance to 1942 prototypes, though basic principles remained unchanged. Better ventilation, stronger fasteners, improved insulation options. Good design became exceptional through use, failure, adaptation, and the patient work of making things better. May 8, 1945. Victory in Europe. August 15, 1945. Victory over Japan. Suddenly, the military owned roughly 170,000 Quonset huts scattered across 6 continents with no clear plan. The original assumption? These were temporary wartime expedients to be scrapped once permanent facilities could be built. But something unexpected happened. Nobody wanted to get rid of them. At hundreds of bases slated for closure, commanders saw not obsolete relics, but perfectly functional buildings costing nothing to maintain, repurposable for virtually anything. The War Assets Administration, tasked with liquidating surplus property, faced an unusual problem. More demand for used Quonset huts than inventory to sell. Veterans returning home discovered housing shortages so severe that families lived in converted chicken coops and shared apartments with 3 other families. The construction industry, starved of materials during war years, couldn't build fast enough. Into this gap stepped the Quonset hut, available at liquidation prices, $1,000 to $2,500 for complete structures that would cost $8,000 to build conventionally. By late 1946, suburban developments made entirely of Quonset huts sprang up around major cities. Roger Young Village in Los Angeles housed 750 families. Vettville developments appeared near universities, where the GI Bill flooded campuses with students needing immediate housing. Architectural adaptation got creative fast. Families added wooden facades to curved ends, transforming military surplus into quirky cottages. Interior walls divided open space into bedrooms and kitchens. Windows got cut into steel sides, violating structural principles but making spaces livable for family life. Some owners buried structures halfway into ground for earth-sheltered insulation. Others connected multiple huts end to end, creating sprawling compounds that grew as families expanded. In Portland, Oregon, an entire neighborhood called Fairview Edition consisted of 350 Quonset homes. Residents planted gardens, painted steel walls cheerful colors, and built conventional-looking porches disguising utilitarian origins. Churches discovered Quonset huts solved different problems. Post-war religious revival and exploding suburban populations needed worship space, but traditional church buildings required decade-long capital campaigns. First Presbyterian Church of Levittown, Pennsylvania, held services in a Quonset hut from 1952 until 1967. The acoustics were terrible, aesthetics underwhelming, but people could gather for worship next month instead of next decade. Some temporary church huts remained in service 30 years. Education saw similar adoption as baby boom school enrollment exploded. Districts needed classrooms immediately, but conventional schools took years to construct. Rural districts especially embraced Quonset classrooms. A single hut provided space for 30 students at 1/10 traditional construction cost. By 1950, temporary hut-type buildings, many of them surplus Quonsets, had become a familiar sight at U.S. colleges, veteran housing projects, and fast-growing school districts, simply because permanent brick schools could not be built fast enough. Commercial sectors recognized clear span space without internal support columns, perfect for industrial work. Agricultural use proved especially popular. Thousands of Midwestern farms added Quonset storage buildings. Maintenance was minimal, hose off exterior once yearly, check bolts occasionally. Structures lasted indefinitely. This civilian adoption created accidental architectural legacy. Quonset huts became embedded in American visual culture as symbols of practicality over pretense, function over form, make-do ingenuity. Architectural historians initially dismissed them as temporary eyesores, but by the 1990s, preservationists started recognizing surviving huts as important examples of adaptive reuse. Several achieved historic landmark status. What was supposed to be temporary became permanent in American landscape and memory. When the 2010 Haiti earthquake destroyed Port-au-Prince, relief organizations faced the same equation American military planners confronted in 1942. Immediate shelter for hundreds of thousands, no existing infrastructure, no time for conventional construction, conditions destroying inadequate temporary housing within months. The solution that emerged borrowed directly from Quonset principles: arched steel frames, corrugated metal panels, prefabricated components shipping flat and assembling quickly. The formula hadn't changed because underlying physics and logistics hadn't changed. The United Nations currently uses shelter systems called RHUS, Refugee Housing Units, essentially Quonset huts with 80 years of material science improvements. Instead of corrugated steel, they use insulated composite panels. Instead of bolt-together assembly, snap-fit connections. But the core concept remains identical. curved profile for structural efficiency, self-supporting arch eliminating internal framing, flat-pack shipping, assembly by unskilled labor with minimal tools. A two-person crew can erect a modern RHU in 4 hours, almost exactly matching 1942 Quonset specifications. These units currently house over 200,000 displaced persons in refugee camps across Africa, the Middle East, and Asia. After Hurricane Katrina devastated the Gulf Coast in 2005, engineers studying which buildings survived found curved structures consistently outperformed rectangular ones. Mississippi Coast neighborhoods saw conventional homes reduced to foundation slabs, while Quonset-style metal buildings stood intact with minor damage. This evidence triggered research into aerodynamic architecture, designing buildings working with wind forces rather than resisting through brute strength. The result looks remarkably like a Quonset hut because the physics haven't changed. The modern tiny house movement unknowingly reinvents Quonset principles when seeking maximum space with minimum materials and cost. Several companies now manufacture arch-roofed prefab cabins using the same corrugated metal and self-supporting curve Brandenburger pioneered. Some high-end architectural firms have rehabilitated the aesthetic, designing luxury versions with floor-to-ceiling glass end walls and premium finishes costing $300 per square foot, while maintaining the signature curved profile. The arch has gone from utilitarian necessity to design statement. Military applications never stopped. United States Armed Forces still deploy arch-style shelters in conflict zones. Current specifications call for helicopter liftable units assembled in combat conditions, surviving IED blast waves. Materials evolved: aluminum alloy frames, Kevlar reinforced panels, climate control systems. But show a 2025 military shelter to the 1942 Quonset Point team, and they'd immediately recognize their own design philosophy. Recent innovation includes expandable versions deploying from shipping containers, unfolding like origami, locking into rigid arch structures within an hour. The economic argument justifying Quonset huts in 1942 remains compelling today. When disaster strikes or rapid deployment is required, conventional construction cannot compete on speed or cost. Modern engineered arch shelters deliver weather protection for approximately $50 per square foot, including shipping and assembly. Conventional construction in same locations costs $150 to $300 per square foot, requiring months instead of days. For humanitarian organizations on donor funding or military logistics managing trillion-dollar budgets, this cost differential matters enormously. The math-driving Quonset development, shelter the most people for least money in shortest time, hasn't changed because scarcity economics haven't changed. Perhaps the ultimate validation comes from space exploration. NASA and private space companies designing Mars habitats keep arriving at Quonset-like solutions. Arched profiles resisting dust storms, prefabricated components shipping on spacecraft, self-supporting structures not requiring extensive foundation work. Interplanetary construction constraints mirror Pacific Theater challenges of 1942 so precisely that engineers independently rediscover the same solutions. When humans finally build permanent shelters on another planet, there's reasonable chance those structures will owe design heritage to 30 engineers working in a Rhode Island warehouse during World War II's darkest days. From Guadalcanal to Mars, the answer remains the same. 3 principles emerged from that Rhode Island warehouse in 1942, principles remaining as valid today as when Otto Brandenburger first sketched them. First, eliminate what fails. Brandenburger's team learned this when they abandoned the idea of a wooden floor after field tests showed it was the slowest piece to assemble and the first to rot in island humidity. Removing it cut 1,200 pounds and saved 6 hours of assembly time. Second, design for constraints, not against them. The engineers had no luxury of cement foundations or heavy machinery, so they treated those limits as part of the design. Panels had to fit a standard railcar and be lifted by 4 men. The constraint became the blueprint. Third, let physics do the work. When they realized a slight curve could make wind slide away instead of punching through, they stopped fighting nature and used geometry as their ally. Every bolt shared the load. The arch carried itself. April to June 1942. 60 days. 30 engineers in one warehouse with an impossible deadline. They created something housing millions, surviving conditions destroying permanent buildings, continuing to influence design 8 decades later. Not because they were smarter than modern engineers, they had pressure forcing brutal simplicity. Every unnecessary component meant heavier panels, longer assembly, higher cost, more failure points. They stripped away everything non-essential until left with the absolute minimum that would work. In that enforced simplicity, they found something approaching perfection. John lapsoliu mid morting hin chin tram bon moi bon tren mot tram sao moing hin John vi morting hin ba tram chin moi bon tren mot fan moi chifi jam bi xoao jai. When Admiral Nimitz visited Guadalcanal in late 1942, reports suggest he stood in a Quonset hut that had survived 3 bombing runs, a typhoon, and months of jungle rot. Running his hand along the corrugated steel, he may have observed, "Remarkable what pressure can produce." He wasn't just talking about the structure, he was talking about American engineering under impossible pressure, forced to be brilliant because adequate wouldn't suffice. The Quonset hut worked because it had to work. In that necessity, Brandenburger and his team created something accidentally permanent while trying to build something intentionally temporary. Perhaps the deepest lesson. Sometimes the best way to build something lasting forever is focusing entirely on making it work right now. Solve for real conditions, strip away the non-essential, trust that good solutions to real problems remain relevant long after the original crisis passes. The Quonset hut was designed for a war that ended 80 years ago, but its descendants still shelter refugees and disaster survivors. Its principles still guide emergency response. Its DNA still influences architecture from tiny houses to Mars habitats. Because good engineering, honest engineering, solving real problems with elegant simplicity, never becomes truly obsolete. It just finds new contexts and new generations rediscovering what pressure once produced when the world was at war and stakes couldn't have been higher. The huts remain scattered across America, and the world, silent testament to what's possible when necessity forces ingenuity, when pressure produces brilliance, when men faced with impossible problems simply solve them anyway. That's the American story. Not perfection, but practical problem-solving. Not elegance, but effectiveness. Not what's ideal, but what actually works when everything's on the line. The Quonset hut embodies that story in corrugated steel and brilliant simplicity. 80 years later, when disasters strike and emergencies demand rapid response, engineers still find themselves reinventing what 30 men figured out in 60 impossible days. Some solutions are timeless. Some answers don't change. The arch still stands. The principle still works. If you enjoyed learning how American engineers solved impossible problems under pressure, subscribe to our channel for more untold stories of innovation that changed history. Every week, we bring you the remarkable tales of how ordinary people created extraordinary solutions when the world needed them most.